Lesson 23 deals with an infinite series. By definition, an infinite series is the sum of an infinite sequence of numbers, such as a1 plus a2 plus a3 and so forth. The goal of this section is to understand the meaning of such an infinite sum and to develop methods to calculate it. For this example, we have 1, then 1/2, 1/4, 1/8, and etc. So it looks like this partial term, the general value looks like this. And if we take the limit of this partial sum, then it actually goes to 2. Anytime an infinite series or the sequence of partial sums goes to a certain number, then we say that that series converges. As it says here in the definition, if the sequence of partial sums converges to a limit L, we say that the series converges and that its sum is L, or the limit. If the sequence of partial sums of the series does not converge, we say that the series diverges. A special series that you'll be dealing with a lot is a geometric series. And it's in the form, the sum going from 1 to infinity of a times r raised to the n minus 1 power, in which a and r are both fixed real numbers. And just a by itself in the very front is the first term of the series, and r is the ratio going throughout the series. Your ratio can be positive or negative, and the ratio can actually help you determine if a geometric series converges or diverges. The geometric series has its own set of rules for determining convergence or divergence. If the absolute value of r is less than 1, then the geometric series converges to the partial sum a over 1 minus r. If the absolute value of your ratio is greater than or equal to 1, then the series diverges. Let me introduce to you the first test for a divergent series, and it's called the nth term test. If your series, when you take the limit, if you take the limit as n approaches infinity and your series fails to exist or is different from 0, then that means your infinite series diverges. So let's look at this example 6, and let's take the limit as n approaches infinity of our series. Now, anytime you take the limit as n approaches infinity, if the numerator and denominator's exponents are the same, then you can take the ratio of the numbers in front of the letters. So 1 over 1 is equal to 1. And because that is different from 0 according to our nth term test, then that means the series diverges. Let's look at some other examples. Part A, this series clearly diverges because if you take the limit as n approaches infinity of n squared, then Infinity squared is still infinity, and that means our limit fails to exist or is different from 0. So the series in part A diverges. We did part B earlier. Part C, let me explain why this series does not exist. Let's write out some of the first few terms. And I'm just plugging in 1, 2, 3, and 4 for n, respectively. The first one, -1 squared, is 1. -1 to the third power is -1. -1 to the fourth power is 1. And finally, -1 to the fifth power is -1. Our series bounces back and forth between -1 and +1. So it's not going to converge to one specific and one specific value. Or you could say that this series is oscillating between values. So this series diverges. No test was really needed here. You just listed a few of the terms in your series to determine a pattern. Let's look at the next problem. Using the nth term test, we'll take the limit as n approaches positive infinity of our series -1n over 2n plus 5. And recall, when you take the limit as n approaches infinity, and if the numerator and denominator exponents are equal, to find the limit, you just take the ratio of the coefficients in front. So our limit is -1/2. And because that is different from 0, then that means our series diverges. For the next example, or next few examples, we have to write out some of the first few terms of our given series and then determine the sum, determine if it's convergent or divergent. As you see here, to find the first term, you plugged in 0, and that gives us 1 for the first term, or A. To find the second term, you plug in 1 for each n, and that gives you -1/3. Now, it looks like this may be a geometric series. How we can tell is we can actually rewrite our series as -1/3 to the nth, all to the nth power. And -1/3 is our ratio. But if the ratio is not so obvious, then the simple way to find the ratio is just take your second term in the sequence and divide it by the first term. So that also gives us the ratio -1/3. Now we can actually find the sum, because according to geometric series, if the absolute value of our ratio is less than 1, which is the case here, then our series converges. So let's find the sum. And the sum formula is A over 1 minus R, in which A is the first term in your series. So that would be 1 over 1 minus negative 1/3. And that gives us 1 plus 1/3. Now, an easy way to simplify a complex fraction is multiply the entire fraction by your least common denominator, which in this case is 3. Now right here the 3's cancel out and you're left with 1. So the sum of our series is 3/4. So the sum of our series, as I was saying, is 3 over 4. Let's look at another example. Write out the first 4 terms of the series to show how the series starts, then find the sum of the series or show that it diverges. This looks like a geometric series. We can rewrite the first fraction as 10 times 1/3 to the nth power. And the second fraction can be rewritten as 4 times 1 over 5 to the nth power. So we have a geometric series. The ratio of the first part is 1/3, and the ratio of the second part is 1/5. Now for both ratios, it satisfies the condition of being convergent, because if we plug in 1/3, well, 1/3 is less than 1, that's true. And if we plug in 1/5, 1/5 is less than 1 is also true. So this series converges, and that means we can find its sum. So our sum formula is A over 1 minus R. And one thing I need to go back and find is A for each fraction. Well, if you plug in 0 up here, 1/3 to the 0 power is 1, times 10 will give us 10 for A, for the first fraction. And right here, when you plug in 0 for N, 1/5 to the 0 power is 1, times 4, so 4 is our first term in that second fraction. And R is 1/5. Again, a simple way to reduce a complex fraction is multiply the entire complex fraction by your least common denominator. So for the first complex fraction, that is 3. So that simplifies to 30 over 3 minus 1. And that gives us 15 for the first half of our sum. And for the second complex fraction, multiply everything by 5. And that gives us 20 over 5 minus 1, which is 5. So the sum of our entire series is 15 plus 5, or exactly 20. I'm not going over this next example because it's similar to what I just worked out. But this problem is actually a view an example question in my math lab. So when you get a chance, take a look at it. Question 4, determine if the series converges or diverges. If the series converges, then find its sum. It's easy to tell the ratio of our series is 1/12. And A, or the first term in our series, is also 1/12. To test for convergence for a geometric series, we take the absolute value of our ratio and see if it's less than 1. 1/12 is less than 1, so our series converges and we can find its sum. So let's write down our sum formula. S is equal to A over 1 minus R. And let's plug in A and R respectively. Again, a simple way of reducing our complex fraction is by multiplying the entire complex fraction by the common denominator, which in this case is 12. Cancel out your 12s, and you're left with 1 over 12 minus 11. So the sum of our geometric series is exactly 1 over 11. The next example, we're not determining convergence or divergence. We're given a repeating decimal, and we need to express this repeating decimal as the ratio of two integers. So I'm going to let x equal to 0.17 repeating. Multiply both sides of our equation by 100. So we have 100x. And when you multiply 0.17 repeating by 100, our decimal moves 2 places to the right. So that would be 17. But don't forget, after that decimal point, the 1 and 7 keeps repeating. Subtract everything is the next step. So 100 minus 1x is 99x. And on the other side, the 0.17s cancel out, repeating, leaving us with just 17. And the last step, divide both sides by 99. So 0.17 repeating is actually equal to 17 over 99. And you can check this with the calculator. 17 over 99 does give us 0.17 repeating. Going back to testing a series for if it's convergent or divergent, let's look at a trig problem. Determine if this series is convergent or divergent using the nth term test. take the limit as n approaches infinity of cosine of 14 over n. In place of n, plug in infinity. Any number over infinity, or a very, very large number, gets very, very close to 0. So we have cosine 0, which is 1. Per the nth term test, if we get anything other than 0 for our limit, or the limit fails to exist, then our series diverges. The next example, we have the same directions, but this involves a natural log. So we take the limit as n approaches infinity of natural log of 1 over n. And where you see an n, plug in infinity. So 1 over infinity is still 0. And if you were to graph this series in Desmos, as n goes to infinity, your limit is actually going towards negative infinity. In other words, our limit fails to exist. So our series diverges. Let's look at some more examples. I'm skipping 9, but this is also a view and example question in my math lab. The same for number 10 and number 11, so you can look at those steps on your own. We haven't done one yet involving e, base e, so let's look at number 13. Determine whether the series converges or diverges, and if it converges, then find its sum. Let's rewrite this series as 1 over e to the 4nth power. And we can actually rewrite that as 1 over e to the 4th, all raised to the nth power. We have a geometric series. Our ratio is 1 over e to the 4th power. And for a geometric series to test convergence, take the absolute value of your ratio and see if it's less than 1. And when you put 1 over e to the 4th in your calculator, it is indeed less than 1. So our series converges, and that means we can find the sum. The first thing we need to find, though, is the first term in our sequence, or a. So if we let n equal 0, that would equal to positive 1. So our sum formula is a over 1 minus r. And just plug in your a and r. So we have 1 over 1 minus 1 over e to the 4th power. To simplify a complex fraction, again, multiply the entire complex fraction by your common denominator, which in this case is e to the 4th power. Here, the e to the 4ths cancel, And our final answer, or sum, is e to the fourth all over e to the fourth power minus 1. To sum up lesson 23, an infinite series is a sum of a sequence of numbers. A geometric series has a ratio, and a geometric series has its own set of rules to determine convergence or divergence. And another test, or actually the first test, is that we've been introduced to is the nth term test. And basically, when you're taking the limit as n approaches infinity of your series, if you get a limit that fails to exist or is like infinity or negative infinity, or you get a limit that's different from 0, then according to your nth term test, the series diverges.